Hello, today we are finishing with viscosity. This is the last part of this small saga on viscosity, and today we will talk about normal and shear stresses, and we will express them in the terms of second Newton's law. I will start this video by demonstrating using this experimental platform the main idea behind these two types of stresses. Here I have a dough mix of flour and water that I made in a approximately rectangular shape. Well, now, so what is the idea of normal stress? Normal stress is if I apply force normal to one of the faces. Imagine two molecules on this face that is pointing to you. As I apply normal force, which is called normal stress, I am expanding this dough, and the relative position of these molecules expanded. They are further from each other than they were before. At the same time, if I return this to the original spherical shape, I can apply different type of force called shearing force. So here I don't press down, I press on the side, and look how I'm literally shearing this dough, and now the position of the molecule along the height relative to each other changed. Of course, I can twist this over some angle, and in the most complicated case, I can press down, shear, and twist at the same time. These three combined motions represent normal and shear stresses. Normal stress pushing down, shear stress when I apply shearing force over this. Here I used analogy to visualize something that I cannot see in the air using something I can see, this dough. However, at some point the analogy fails. And please let me know in the comment section below where the analogy between dough and air actually fails. I need to wash hands from the dough. What we need to do now for the rest of this video is we need to derive the normal and shear stresses that arise due to and the forces that arise due to viscosity, and we need to express this in terms of second Newton's law. There is a lot of mathematics in today's video, but that's just how the things are. Viscosity is complicated, and I told you throughout this series that viscosity is more complicated than ordinary, for example, pressure gradient force. So, grab your favorite beverage and enjoy the synchrony of mathematics and physics. Viscosity is described through the motion, or these stresses that I talked about are described in terms of tensors. What are tensors? Temperature in this room is around 22 degrees Celsius. This is scalar. Giving you number, I told you everything there is to know about temperature. Wind is a good example of vector. I can say wind speed is 5 meters per second from west to east. That's one component. North component is 1 meter per second from south to north. And let's say it is descending with 0.5 meters per second from some elevation. So, giving you these three numbers, I explained entirely wind. Tensors that I will represent with S, arrow S that goes down, are described in terms of actually 9 numbers, and that is usually put in a matrix form like this. So let's say some numbers 1, 2, 7, I don't know, 2, 2, 5, 7, 5, 3. So these numbers describe tensor S, and why do we put them in a matrix form? Because if I change reference frame, then all these numbers are adjusted using the rotation matrix, so that, for example, if they represent some force or something, the force is always the same no matter what reference system you're using. Okay. Now, action of viscosity is represented through the stress tensor. And the stress tensor is related to strain. Now, what is strain? Well, let's first look at our example of dough that we substituted to be air, that I compressed down. Let's say there were 2 points here, point A and point B. And the distance between these 2 points is delta x. Now, when I stretched this, let's say point A moved here and point B moved here. So this is now A1, B1. Strain is defined in the following way. Let's say the new distance between these 2 points is some delta L. I define strain as delta L minus delta x, so new distance minus all distance, everything normalized with the all distance. But what is this delta L? Well, this is where the point was before, point A before stretching, point B before stretching. Clearly, distance delta L is the all distance plus this part minus this gap here. So, all distance is delta x plus this part. Well, this part is velocity at point B in time interval delta t minus this gap here, and this is velocity of point A in the time interval delta t, and everything is divided by delta x and minus delta x. This delta x here. Now you can see that delta x and delta x cancels out, and I can move delta t to the other side, so I will get that strain over delta t is equal ub minus ua over delta x. In the limit, when delta x and delta t go to 0, this delta t go to 0, I get that d of strain, or rate of change of strain over time dt is delta u over delta x. This is the motion of strain when we have normal stresses. Now let's see what we get if we have shear stress applied. If we have shear stress applied, let's again look at the case of this rectangle. And now I applied shear stress. So let's say this is point O, this is point A, and this whole cube gets this new position, something like this. So I clearly didn't just compress it, I applied some shear force on it. There is this angle alpha, and there is this angle beta. Alpha is angle between old OA and OA1, and beta is between OB, let's say, and OB1. Let's see what this alpha represents. Tangent of this angle alpha is Well, it is opposite side, and the opposite side is velocity v. So if this is my x direction and this is my y direction, velocity v of point A in time delta t divided by the adjacent side. Well, what is adjacent side? It is the original distance. Let's say this is delta x, this is delta y. So delta x plus the amount by which this point A moved towards the right. And this is u a delta t. Now I will take advantage of the fact that this angle is very small and these distances OA and also OB are very, very small, infinitesimally small, so I can expand them in terms of Taylor series in respect to point O. And I will get that tangent alpha is equal. VA becomes what? Well, it becomes velocity at O, but I assume that is 0 plus the rate of change of V along the x. So that is delta V over delta x times distance delta x and times delta t divided by delta x plus I do the same for u. So that is delta u over delta x times delta x times delta t. Now I also told you that alpha is very, very small, so tangent alpha is similar to alpha. So this small alpha, let's call it delta alpha. I move t to the other side from here is equal, well, I am left with delta v over delta x divided by, you can see that delta x cancels everywhere, divided by 1 plus delta u over delta x times delta t. Now I will set my delta t to go to 0, and you can see that the left side of this expression in that case becomes d alpha over dt, and the right hand side, well, 1 is a constant. If this goes to 0, then this becomes infinitesimally small compared to 1, and then I can neglect this term as a higher order term. So this becomes delta v over delta x. Using the same reasoning, I can derive rate of change of beta. d beta over dt is equal delta u, delta u over delta y. Therefore, the combination of these two, d over dt, alpha plus beta, is equal, well, it is equal delta v over delta x plus delta u over delta y. And this is the strain rate in the case of shearing force. Now you might say, what happens if you subtract these two? If you say d over dt of alpha minus beta, what do you get then? Then you get dv dx minus delta u over delta y. And what is this quantity? Well, this quantity is rotation. And when we have pure rotation of a body, there is no strain. Now, we need to relate these strains to stresses. And this is how we do it. I will take the same cube I analyzed before. I will just make it a little bit bigger. And what are my stresses? Well, I said if I look at this face that is looking at me, this forward face, then there is normal stress, tau xx, we call it. So this is my x direction, this is my y direction, and this is my z direction. Then there is one shearing stress, tau yx, and there is tau zx. So, as you can see, these are stresses along the principal components. The same happens on this face over here, that is this face. I have tau y, this is normal stress on the face that has unit vector in the positive y direction. Then I have tau zy, and then in this direction I have tau xy. And the same happens for this top face. I have tau zz, normal stress. I have shear stress in the y direction and one shear stress in the x direction. The figure quickly becomes very busy, but if you followed me all the time, you know what I'm talking about. And we represent all these 9 components of the shear stresses in terms of tensor S that has the components tau xx, tau yx, tau zx, tau xy, tau yy, tau zy, tau xz, tau yz, and tau zz. Please notice that the normal stresses are on the diagonal. These are normal stresses. And the shear stresses are the off-diagonal elements. We also said in the previous videos on the Newton's law of viscosity, link is in the description, that in the case of Newtonian fluid, stress is proportional to the proportionality constant for stresses is this dynamic coefficient of viscosity mu. So I can multiply this with mu to get my Newtonian stresses on my Newtonian fluid. Now, each of the rows represents force per area, or the total stress on each of these faces of this cube that I plotted here. We can quickly demonstrate that. To find stress vector, I take normal on one of these faces and I do dot product with this stress tensor. As a quick example, if I want to extract stresses on this face that has unit vector k, or in the vertical direction, I would say this is normal is k, 0, 0, 1, dot product with this s, and I will get, of course, that the result is tau xz, tau yz, tau zz, if I multiply this unit vector with this tensor. Okay, the next thing we need to know is that shear stresses are symmetric. That means that tau xy is the same as tau yx, that tau zx is the same as tau zx, and that tau yz is the same as tau zy. This can be explicitly proven, but I'm not going to do it for the sake of time. There are very special cases when this is not necessarily true, but this happened if there is some internal volumetric torque on fluid elements, and that sometimes can happen in some magnetized flows. But we are not dealing with these things in atmospheric science. So let's now write this matrix in terms of our stress tensors in the explicit form. So stress tensor becomes, now, what is it? Well, the first term we saw in the previous on the previous page of derivation is the normal stress, and that one becomes 2 delta u delta x. The second term is, we derived it explicitly, delta v delta x plus delta u delta y. And the third term becomes delta w delta x plus delta u over delta z. Then I'll put diagonal terms first. This one is 2 delta v over delta y, and this one is 2 delta w over delta z. And the term here is delta w over delta y plus delta v over delta z. Because my shear stresses are symmetric, I don't have to write this bottom part of the matrix because it's the same as this. So I can say it's the same as this top part. This is the stress tensor, and at the end of this video we need to put this stress tensor in the framework of the second Newton's law. Because by now, if you are still here, you might say, okay, I understood some parts, I didn't understand other parts, but can you just tell me how do I use this business of stresses in terms of the second Newton's law? Because the second Newton's law is how we represent action of forces. And this is exactly what I will tell you now. To do so, we will for the very last time look at our big cube that has these faces with the length delta x, delta y, and delta z. And I will represent stresses on each face of this cube by referencing them to this point over here. Okay? So this is my x, z, and y direction. Now I will say that on this first I will cover faces in the x direction. On this face, let's say I have stress tau xx, normal stress. On this face, because delta x is very small, I will again use Taylor series approximation. This is tau xx plus delta tau xx over delta x and times this distance delta x. Now let me take perhaps different color. I will use red color for this bottom face. Let's say bottom and top. Let's say at the top I have a shear stress tau zx, and on the bottom I have a shear stress tau zx plus, this will become very busy but stay with me, delta tau zx over delta z times delta z. Probably you cannot see what I wrote here, but if you are listening what I'm saying, then you will understand. And in the x direction, I also have shear stress on this face that is close to me, face on the cube. I'll use blue color. And in this direction, I have tau yx, and in the opposite direction, on the far side, I have tau xy plus delta tau xy over delta y times delta y. Okay, what is left now is that we write, because remember that each stress represents force per unit area. So what we need to do is to write down second Newton's law in the x direction. It says that mass times acceleration in the x direction is the sum of all forces in the x direction. What is the mass of this? What is the mass of this cube? Well, mass of this cube is density times the volume. Volume is delta x, delta y, delta z, times acceleration in the x direction is the sum of all forces. First, I will take normal stresses. so tau xx plus delta tau xx over delta x times delta x. In the negative x direction I have minus tau xx, and I have to multiply with area. Area of this side is delta y delta z. Now I add plus, I add my shear forces, tau yx, so I am collecting my shear force, blue one basically, tau yx plus delta tau yx over delta y times delta y minus, in the opposite direction of the x-axis, tau yx, and then the area is delta x delta z. Lastly, I have tau zx, so I am collecting the red one, plus delta tau zx over delta z times distance delta z, and minus the one that is going in the opposite direction of the x-axis, tau zx delta x delta y. I hope you can see that these cancel out, that when I bring delta x here I get volume, delta y here gives me volume, delta z here gives me volume, so I can cancel these guys with the volume on the left side. And now I am getting that, let's write it here, I am getting that rho times acceleration in the x direction, that is du over dt, is equal delta tau xx over delta x plus delta tau yx over delta y and plus delta tau zx over delta z. And this is the second Newton's law expressed in terms of stresses. Second Newton's law in the x direction. Clearly, I can do the same reasoning in the other two directions, namely y and z. Now, to finish this whole thing, we need to go back to our stress tensor and express all of these. So substitute these instead of these taus. So what I will get if I do that is rho du dt is equal. Now this is Newtonian fluid, so I have this coefficient of proportionality mu, which is dynamic coefficient of viscosity, because I'm doing this for air, and then I'm getting, multiplies everything, delta x of tau xx, we said it is 2 delta u over delta x plus delta y, tau yx was delta v over delta x plus delta u over delta y and plus delta z, tau zx is delta w over delta x plus delta u over delta z. Now you can rearrange these terms to get this. Rho du dt is equal mu, that multiplies delta second u delta x square plus delta second u delta y square plus delta second u over delta z squared plus mu delta x of delta u per delta x plus delta v over delta y plus delta w over delta z. What I'm saying is that this right-hand side is exactly the same as this right-hand side. I just rearrange terms. Finally, I can put this in the vector form now to generalize to all three directions, not just u component, and then this will become rho du over dt is mu, this is nabla squared v plus nabla dot v, and this mu, coefficient mu, but I actually have to add mu prime. Now, why is this? Well, this is because this term over here is divergence, as you can see. And if the fluid is incompressible, then this term collapses to zero. So, most of you probably never even saw this term. This is the equation of motion most of you saw, where the viscosity is represented through the Laplacian of velocity, and you never saw this term. And you never saw this term because you are not dealing with shock waves, explosions, or any substances or phenomena where density and velocity field and pressure field change very, very rapidly. If this is the case, if you are dealing with such phenomena, then you have to actually preserve this term in your equation of motion. And then it turns out, this is experimental evidence, that this term comes with modified viscosity, mu prime, and that mu prime is called second coefficient of dynamic viscosity that modifies our original one. But we will never use this term in our atmospheric science business, so this is the equation of motion that accounts for viscosity. At the end, a small remark. In some books, in many books in fact, you see pressure term as a diagonal term that contributes to normal stresses, and this is correct, there is nothing wrong with that. However, I decided to omit this term because it doesn't contribute much to our knowledge on viscosity, and this term results in the pressure gradient force, which I already derived in a separate video. So I decided to omit it here in order to make this derivation at least a little bit easier. So now I really don't have anything else to say about viscosity, at least for now. I hope you enjoyed this saga, that you learned about viscosity, and at the end I give you a full-scale demonstration of viscous forces. Thank you for watching. I feel a light breeze and I can see waves on this lake. The interaction between this wind and the lake is thanks to viscosity, viscous forces. Here we don't have no slip boundary condition at the surface. Here we have two fluids interacting at the interface between water and air. Viscosity is the force that is responsible for their interaction. I hope you can also now visualize an imaginary volumes of water and air being deformed very close to the surface of the water and the surface of the air due to viscous forces. And you can imagine normal and shear stresses acting on both fluids, water and air. The deformation in air is higher because viscosity of air is smaller than the viscosity of water. So much nature, so much physics going on, so much atmospheric science.